Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the grand narrative of mathematical history, certain figures emerge with a brilliance that transcends geographical and cultural boundaries, their discoveries echoing the fundamental truths of the universe. Within the unique intellectual ecosystem of 17th century Japan, a period of deliberate national seclusion, one such mind illuminated the landscape of indigenous mathematics, or Wasan. This was Seki Takakazu, a samurai and mathematician whose insights rival those of his most celebrated European contemporaries. His contributions stand as a powerful testament to the universal nature of mathematical inquiry, demonstrating how profound discoveries can arise in parallel, shaped by distinct cultural and intellectual traditions. We begin our exploration of his genius with the area where his originality first shone with breathtaking clarity: his formulation of a general theory for solving systems of equations, a method that anticipated the development of determinants in the West by a decade. The intellectual roots of Seki's work extend deep into the soil of classical Chinese mathematics. For centuries, scholars in East Asia had grappled with problems presented in texts like the 9 chapters on the mathematical art, which offered practical methods for solving systems of linear equations with up to 3 variables. These ancient methods, while effective for specific cases, lacked a general, extensible framework. They were recipes for solutions, powerful yet conceptually constrained. The challenge that captivated Seki was the creation of a universal tool, a systematic procedure that could handle any number of equations and variables, including those involving polynomial expressions of higher degrees. He sought to move from specific answers to a comprehensive theory of elimination, a way to distill the essence of a complex system into a single, decisive value. His monumental achievement appeared in his 683 publication, Kai Fukidai no Ho, which translates to Method of Solving Fukidai Problems. The term Fukidai referred to problems involving systems of equations, often presented with concealed or implicit relationships. Within this work, Seki unveiled a systematic process for eliminating variables that is, in its essence, the theory of determinants. He developed a unique notation using writing rods, or sanki, and later a form of character-based algebra called boshoho, to represent the coefficients of his polynomial equations. This allowed him to manipulate them with abstract precision. To understand his method, consider a simple system of 2 linear equations with 2 unknowns. For instance, a times x plus b times y equals c, and d times x plus e times y equals f. Seki would arrange the coefficients of the variables a, b, and e into a rectangular array. He then articulated a clear rule for calculation. One would multiply the coefficient by the coefficient e, and from this product, subtract the product of the coefficient b and the coefficient e. The resulting number is what we today call the determinant of the coefficient matrix. He then showed how this value, along with similar calculations involving the constant terms, could be used to find the values of x and y directly. His true genius, however, became apparent in his generalization of this process. For a system of 3 equations, he demonstrated how to expand the 3x3 array of coefficients. He formulated the rule of Serres, calculating the sum of the products of the 3 main downward diagonals and subtracting the sum of the products of the 3 upward diagonals. More profoundly, he described a general method for larger systems, what is now known as Laplacian expansion or cofactor expansion. He understood that the determinant of a large system could be found by combining the determinants of its smaller subsystems, and he correctly articulated the alternating pattern of positive and negative signs required for this expansion. This conceptual leap from a simple 2x2 calculation to a recursive, general formula for any size system represents a monumental intellectual achievement. Seki published this comprehensive theory in 683, a full 10 years before Gottfried Wilhelm Leibniz in Europe would outline a similar idea in a private letter, a letter which itself remained unpublished for many years after. The immediate impact of Seki's determinant theory on Wasan was transformative. It provided Japanese mathematicians with an exceptionally powerful tool for tackling problems of a complexity that was previously unmanageable. His most distinguished student, Take Katahiro, absorbed these methods completely. Take would later leverage this advanced algebraic framework in his own pioneering work on infinite series and the rectification of the circle, where he achieved a calculation of pi to an astonishing 41 decimal places. Seki's method of elimination gave Take and others the algebraic machinery necessary to manipulate the complex polynomial expressions that arose in their geometric and analytic investigations. The school of mathematics that grew around Seki was founded upon this new, powerful algebra. Today, the concept of the determinant remains a cornerstone of linear algebra, a field indispensable to virtually every branch of science and engineering. It is used to solve vast systems of linear equations that model everything from electrical circuits to economic behavior. In physics, determinants appear in the calculation of the cross product of vectors and in describing rotational transformations. In statistics, they are fundamental to understanding the geometry of data and the properties of multivariate distributions. The value that Seki Takakazu first systematically described, born from the intellectual traditions of East Asia and the challenge of ancient problems, has proven to be a universal mathematical constant essential for describing the relationships within linear systems. His work serves as a compelling example of a fundamental mathematical idea discovered independently, a testament to a shared human capacity for abstract reasoning. This mastery over finite algebraic systems, however, was merely the foundation for Seki's next great intellectual ascent. Having developed the tools to solve complex equations, he turned his attention toward the ultimate challenge of the infinite, leading to his own remarkable development of the principles of calculus. His mastery over finite algebraic systems, however, was merely the foundation for Seki's next great intellectual ascent. Having developed the tools to solve complex equations, he turned his attention toward the ultimate challenge of the infinite, leading to his own remarkable development of the principles of calculus. This pursuit was born from a set of problems that vexed mathematicians globally during the 17th century. The precise measurement of a curved line, the exact area of a figure bounded by a curve, and the true volume of an irregular solid were challenges that lay beyond the grasp of classical geometry. In Japan, this quest had a specific heritage rooted in the concept of yenri, the circle principle. For generations, Japanese mathematicians, or Wasan scholars, had pursued the accurate calculation of pi by approximating the circle with polygons of an ever-increasing number of sides. This method of exhaustion, a process of getting closer to a true value through successive steps, was the intellectual soil from which Seki's greatest contribution would grow. Seki Takakazu inherited this tradition of polygonal approximation, a method used with great success by his predecessors like Muramatsu Shigeyo to calculate pi to many digits. He perceived within this specific technique for circles the seed of a universal method. His profound insight was to abstract the core process, transforming the circle principle into a far more powerful and general methodology he named yenri, which translates roughly to the circle principle method, though its scope was vastly broader. The yenri was an algorithmic framework for solving problems of rectification, quadrature, and cubature, the classical terms for finding the length of curves, the area of curved shapes, and the volume of solids. It was a calculus, but one conceived with a distinct character and philosophy, built upon an algebraic and iterative foundation. The operation of the yenri method reveals a mind of extraordinary computational and conceptual power. To find the area under a curve, for example, Seki would dissect the area into a series of thin rectangular strips, a technique familiar to his European contemporaries. He would then calculate the sum of these areas. The next step, however, showcased his unique genius. He would repeat the calculation with double the number of strips, yielding a more accurate approximation. He would do this again and again, generating a sequence of values that crept ever closer to the true area. Instead of continuing this laborious process indefinitely, Seki analyzed the sequence of approximations itself. He discovered that the errors in each successive step decreased in a predictable geometric ratio. This discovery allowed him to invent a breathtakingly clever algebraic shortcut. By setting up equations that described the relationship between his successive approximations, he could systematically eliminate the terms representing the error. This technique, which scholars today recognize as a form of Richardson extrapolation or Aiken's delta squared process, allowed him to leapfrog over an infinite number of steps. He could take a few initial, imperfect calculations and from their pattern derive the exact value they were tending toward. It was a method of accelerated convergence, an algebraic portal to the limit. He was, in essence, using algebra to solve an infinite process, a starkly different approach from the motion-based fluxions of Isaac Newton or the formal symbolic logic of Gottfried Wilhelm Leibniz. When placed alongside the calculus developing in Europe, the work of Seki presents a fascinating case of convergent intellectual evolution. Newton conceived of his fluxions through the lens of physics, imagining quantities as flowing and their derivatives as their rates of change. Leibniz built a majestic and powerful symbolic system, the familiar integral and differential notation, which captured the logic of infinitesimals with unparalleled elegance and generality. Seki's yenri was different yet again. It was fundamentally algorithmic, a set of precise computational procedures rooted in the algebraic traditions of China and Japan. His working medium was the sengi, or counting board, and his notation involved inscribed characters, a system perfect for solving specific, complex problems, but less suited for expressing abstract, general theorems. This difference in conceptual foundation is crucial. While Seki's methods allowed him to calculate definite integrals and find derivatives, the explicit formulation of the fundamental theorem of calculus, the profound insight that these two operations are inverses of each other, remains less pronounced in his surviving works compared to those of Newton and Leibniz. His writings demonstrate a practical mastery of the procedures. He could find the tangent to a curve, a process equivalent to differentiation, and he could find the area under it, the process of integration. The philosophical bridge explicitly connecting the two was either implicit in his teaching or articulated in a form unique to the Wasan tradition. The immediate impact of the yenri was immense within the sphere of Japanese mathematics. Seki and his followers applied this powerful new engine to a host of problems that were previously unsolvable. He successfully calculated the surface area of a sphere and the volume of a solid generated by rotating a circular arc around an axis. Using his accelerated convergence methods, he computed the value of pi to an accuracy that was remarkable for his time, demonstrating the raw power of his algebraic techniques. The true flourishing of his methods, however, came through his students. His most brilliant disciple, Takakazu, took the yenri and extended it with spectacular results. Take produced the first infinite power series expansion for the square of a circular arc, a result equivalent to the arc sine series discovered in Europe. This was a direct and profound extension of Seki's work, showing how the yenri provided a fertile framework for new discoveries. Take and other members of the Seki school, like Matsunaga Yoshisuke, went on to use these methods to construct vast and detailed tables of trigonometric values and other essential mathematical quantities, forming the bedrock of advanced astronomy and calendrical science in Edo, Japan. The reception and transmission of this knowledge followed a pattern distinct to its cultural context. Seki's discoveries were considered precious, often secret, treasures of his school. This knowledge was passed down from master to disciple, a tradition of hidden or secret transmission, which ensured its preservation, but also limited its widespread dissemination in peer review. The reliance on the counting board and its associated notation, while computationally powerful, created a barrier to the kind of abstract generalization that Leibniz's symbolic language enabled. Consequently, while the Seki school dominated Japanese mathematics for more than a century, its brilliant achievements remained largely isolated from the concurrent mathematical revolution in the West. It stands as a monumental intellectual achievement, a testament to the fact that the complex and beautiful ideas of calculus could be reached through more than one path. Heading forged this powerful engine for navigating the infinite. Seki and his school were now equipped to attack the most challenging problems in classical and contemporary mathematics, turning their formidable new tool toward the intricate world of geometry. Having forged this powerful engine for navigating the infinite, Seki and his school were now equipped to attack the most challenging problems in classical and contemporary mathematics, turning their formidable new tool toward the intricate world of geometry. The world of Wasan, or traditional Japanese mathematics, had long been preoccupied with geometric puzzles. These challenges were matters of public spectacle and intellectual honor, frequently inscribed on wooden tablets called sengoku and hung in the precincts of shrines and temples for all to see. They were a communal display of mathematical prowess, a call for solutions from any mind sharp enough to furnish them. The existing geometric tradition, heavily influenced by Chinese classics like the 9 chapters on the mathematical art, was adept at handling figures composed of straight lines and simple curves. It provided reliable methods for calculating the areas of fields and the volumes of granaries. The true frontier, the source of the most vexing sengoku problems, lay in the measurement of the irregular and the complex, the arc of an ellipse, the surface of a sphere, or the volume of a solid formed by intersecting shapes. It was here that traditional methods faltered, and it was precisely here that Seki Takakazu would demonstrate the profound power of his new mathematics. Seki's assault on these geometric enigmas began with the most fundamental of all curved figures, the circle. The precise value of pi, the ratio of a circle's circumference to its diameter, had been a subject of inquiry for millennia across cultures. Seki sought an approximation of unprecedented accuracy. His method was an extension of the classical approach of Archimedes, yet pursued with a computational determination that was astounding for his era. He imagined a circle with a polygon inscribed within it and another circumscribed around it. By systematically doubling the number of sides of these polygons, he could trap the circumference of the circle between two ever-tightening bounds. Seki carried this process to a breathtaking extreme, calculating the perimeters of polygons with up to 131,072 sides, a figure equivalent to 2 raised to the power of 17. This exhaustive computation, performed entirely with counting rods on a grid, yielded a value for pi accurate to the 11th decimal place. This achievement was a monumental feat of calculation, but the true innovation was the conceptual framework he developed from it, the yenri, or circle principle. The yenri was Seki's key to unlocking the secrets of all curved shapes. In essence, it was a method of exhaustion and a form of definite integration conceived without the symbolic notation of calculus. Seki envisioned a geometric figure, whether a 2-dimensional area or a 3-dimensional solid, as being composed of an immense number of infinitesimally thin slices. For an area, these might be slender rectangles; for a solid, They might be thin disks. By finding a rule that described the size of each slice and then summing this infinite collection of slices, he could determine the total area or volume with precision. This method allowed him to move beyond the simple circle and apply his reasoning to a whole class of previously unsolvable problems. His findings were compiled in works that became foundational texts for his school, including the Kōwa, which detailed his methods for finding volumes. With the yenri as his instrument, Seki systematically dismantled one classic problem after another. He applied it to the sphere, successfully deriving formulas for its surface area and volume that were equivalent to the modern expressions 4 times pi times the radius squared and 4/3 times pi times the radius cubed, respectively. He extended the principle to find the arc length of an ellipse, a far more complex calculation. Perhaps his most elegant and impressive geometric achievement was a solution to a problem that still challenges students today: finding the volume of the solid formed by the intersection of two identical cylinders at a right angle. By slicing the solid, known in modern mathematics as a Steinitz solid, into a series of square cross-sections and summing their areas using the yenri, Seki arrived at the exact answer, 16/3 times the radius cubed. The publication of these solutions, often in response to Sengoku challenges, solidified his reputation as the greatest mathematician in Japan. He had provided what seemed like definitive answers to questions that had stood for generations. The influence of these geometric breakthroughs was immediate and profound within the Japanese mathematical community. Seki's school, the Seki Ryu, became the preeminent center of mathematical learning, and his methods became the new standard. His disciples, inheriting the powerful tool of the yenri, were empowered to push the boundaries of Wasan even further. The most brilliant of his followers, Takakazu, took the circle principle and developed it into a full-fledged method for generating infinite series expansions for mathematical functions. Using the yenri, Take derived an infinite series for the square of a circular arc, a result that mirrors the Taylor series for the arcsine function discovered in Europe decades later. Another prominent follower, Matsunaga Yoshisuke, used Seki's foundational work to calculate pi to 50 decimal places, a testament to the computational power the school now wielded. The geometric work of Seki Takakazu provided the bedrock upon which his successors built a sophisticated and uniquely Japanese form of analysis. Seki's geometric innovations represent a pinnacle of Wasan, a moment where a distinct mathematical tradition, developing in relative isolation, arrived at truths that were simultaneously being uncovered by different means on the other side of the world. His methods, born from the practical challenges of Sengoku and the computational rigor of the counting board, demonstrate that the path to mathematical discovery is manifold. He transformed Japanese geometry from a collection of practical rules into a powerful analytical science capable of describing the continuous and the curved with astonishing accuracy. This mastery over the world of shapes and volumes established a legacy of inquiry that would define Japanese mathematics for more than a century, creating a rich intellectual inheritance for the generations of scholars who would follow in his footsteps. The work of Seki Takakazu provided the bedrock upon which his successors built a sophisticated and uniquely Japanese form of analysis. His geometric innovations represent a pinnacle of Wasan, a moment where a distinct mathematical tradition, developing in relative isolation, arrived at truths that were simultaneously being uncovered by different means on the other side of the world. His methods, born from the practical challenges of Sengoku and the computational rigor of the counting board, demonstrate that the path to mathematical discovery is manifold. He transformed Japanese geometry from a collection of practical rules into a powerful analytical science capable of describing the continuous and the curved with astonishing accuracy. This mastery over the world of shapes and volumes established a legacy of inquiry that would define Japanese mathematics for more than a century, creating a rich intellectual inheritance for the generations of scholars who would follow in his footsteps. Seki's most profound legacy was the establishment of a coherent intellectual lineage, the Seki School or Sekuryu. This is an institution of thought, a shared methodology passed from master to disciple through a tradition of close mentorship and the careful transmission of secret manuscripts. The school's formation marked a pivotal evolution in Wasan. It shifted the intellectual center of gravity from solving isolated, albeit complex, problems toward developing general, powerful, and abstract methods. The core of the Sekuryu philosophy was the supremacy of symbolic algebra, his tendenjutsu, as the ultimate tool for mathematical investigation. This approach allowed his followers to transcend the limitations of purely geometric or numerical reasoning and to probe the very structure of mathematical relationships. This school became the engine of Japanese mathematics, its influence so pervasive that for over 150 years, the story of Wasan is overwhelmingly the story of the Sekuryu and its disciples. At the heart of this intellectual succession stands Takakazu, Seki's most brilliant pupil and the primary inheritor of his vision. Take's relationship with Seki was one of deep intellectual apprenticeship. Upon his master's death, he received the invaluable treasure of Seki's unpublished papers, a collection of insights and nascent theories that would become the foundation for his own life's work. Take's great achievement was to systematize, clarify, and extend his master's pioneering ideas. In his monumental work, the Tetsujutsu Sankei or Compendium of Mathematics, he took Seki's principle of the circle, the yenri, and pushed it to its logical and computational extreme. Using these methods, Take accomplished the astonishing feat of calculating the value of pi to 41 decimal places, a level of precision that served as a powerful testament to the efficacy of the Seki school's analytical techniques. His work went further, demonstrating a profound understanding of the concepts of infinite series that Seki had initiated. Take developed an infinite series expansion for the square of a circular arc, a result that mirrors the work of European mathematicians on power series. This was a direct extension of Seki's foundational inquiries into rectification and quadrature. Through his clear exposition and his own original contributions, Take functioned as the great evangelist of the Sekirai. He transformed his master's dense and sometimes esoteric discoveries into a structured body of knowledge, a formal curriculum that could be studied and built upon by a wider community of scholars. He ensured that Seki's revolution would become a lasting tradition. The influence of the Sekirai, solidified by Take, soon radiated throughout the Japanese intellectual landscape. The school's methods became the gold standard for advanced mathematics. Other schools of Wasan, like the Seijiryu, found their own traditions either absorbed into the dominant Seki paradigm or relegated to a secondary status. This intellectual ascendancy is visible in the very culture of Japanese mathematics. The Sengoku, the beautifully painted wooden tablets bearing geometric problems hung in temples and shrines, began to feature challenges of increasing complexity. These new problems were often constructed in a way that their solution was feasible only through the application of the Seki school's algebraic and analytical machinery. The tablet became both a public showcase for mathematical beauty and a subtle testament to the power of the Sekirayu's advanced techniques. The systematization of this knowledge continued through the efforts of later disciples. The Erma brothers, particularly Erma Rado, played a crucial role in compiling and disseminating the school's teachings. Their publication, the Katsuyo Sanpo or Collection of Important Mathematical Methods, became a canonical textbook for Wasan scholars. It presented the core discoveries of Seki and Take in a comprehensive format, cementing the school's curriculum and ensuring its methods would be the primary language of Japanese mathematics for generations. Through such texts, Seki's intellectual DNA was passed down, shaping the questions mathematicians asked and the tools they used to answer them. For nearly 2 centuries, Wasan developed as a magnificent, self-contained mathematical universe with the principles of the Sekirai as its guiding physics. It cultivated its own aesthetic, valuing elegant solutions and intricate geometric constructions as forms of high art. It developed its own standards of rigor, based on computational verification and the internal consistency of its algebraic system. This period of flourishing isolation produced a body of knowledge rich with unique insights and remarkable discoveries. The eventual arrival of Western mathematics during the Meiji Restoration in the mid-19th century introduced a different framework, one whose deep integration with physics and engineering offered a more potent foundation for modernizing industrial state. Consequently, the tradition of Wasan was gradually superseded in formal education and research. Yet, the legacy of Seki Takakazu and the Wasan tradition he defined endures. It stands as a powerful historical example of a sophisticated mathematical system developing independently of the familiar Greco-European lineage. The study of Wasan offers profound insights into the nature of mathematical discovery itself, revealing that parallel intellectual developments can arise in different cultures to solve similar fundamental problems of quantity, space, and change. The aesthetic elegance of Sengoku continues to inspire, while the unique computational and algebraic methods of the Seki school remain a subject of fascination for historians of mathematics. Seki's work ensured that for centuries, Japan possessed a vibrant, original, and deeply challenging mathematical culture, a testament to the universal human impulse to explore the abstract world of patterns and structures. At the very heart of that impulse, within the unique world of Japanese mathematics, stands the monumental figure of Seki Takakazu. His legacy is the central pillar supporting the entire edifice of Wasan. To understand his impact is to appreciate the profound originality that can flourish within a distinct intellectual ecosystem, developing its own language and methods to interrogate the universe. Seki's story offers a compelling counterpoint to a monolithic narrative of mathematical progress, revealing a path of discovery that ran parallel to, yet remained independent of, the one being forged in Europe. His work serves as an enduring reminder that the fundamental questions of mathematics are universal, even if the cultural tools used to answer them are wonderfully diverse. The genius of Seki Takakazu is most powerfully revealed in his capacity as a system builder. His intellectual ambition went far beyond solving isolated puzzles inherited from Chinese texts. He sought unifying principles, general methods that could transform calculation from a series of ad hoc tricks into a coherent and powerful science. This is the essence of his yenri jutsu, the method of written notation that liberated Japanese mathematics from the physical constraints of counting rods. It is a conceptual breakthrough, creating a symbolic language capable of expressing complex algebraic relationships and enabling manipulations of a previously unimaginable scale. This innovation alone would secure his place in history, for it provided the very grammar that his successors, like Takakazu, would use to write their own mathematical poetry. His exploration of determinants, born from the practical need to solve systems of simultaneous equations, demonstrates this same drive toward generalization. He developed a computational scheme that mirrors the one later formulated by Gottfried Wilhelm Leibniz in Europe. This remarkable instance of simultaneous invention, occurring across continents without any possibility of contact, speaks volumes about the eternal logic of mathematical problems. The structure of linear systems guides the inquisitive mind towards similar solutions, revealing an objective mathematical reality accessible to anyone with sufficient insight and analytical rigor. Seki's work on the subject, culminating in his calculation of determinants for 5x5 systems, represents a pinnacle of algebraic achievement within the Wasan tradition. Similarly, his yenri, or circle principle, showcases a mind grappling with the infinite. His rectification of the circle and his calculation of pi to a high degree of accuracy were accomplished through methods that presage the core ideas of integral calculus. He conceived of polygons with an ever-increasing number of sides, summing the lengths of infinitesimal segments to approximate a curve. This process, conceptually akin to the work being done by Newton and Leibniz, was a home-run Japanese approach to the calculus. It is a tool forged to solve a specific, classical problem, yet it contained the seeds of a much broader theory of limits and summation. The intellectual journey that led him to an expression equivalent to the Bernoulli numbers further cements his status as a pioneer, one who independently uncovered deep and non-obvious patterns within the fabric of mathematics. Evaluating Seki's place in the global pantheon of mathematicians requires a nuanced perspective. A simple comparison of timelines or discoveries with his European contemporaries, while intriguing, misses the larger point. His true significance lies in the demonstration of intellectual autarky. He and the school he founded constructed a sophisticated mathematical world almost entirely from indigenous and assimilated Chinese sources. The resulting tradition, Wasan, possessed its own aesthetic, its own pedagogical methods, and its own set of prized problems. The vibrant culture of Sangvarku, the wooden tablets displaying geometric theorems as devotional art in temples, was a direct outgrowth of the computational power that Seki had unlocked. This fusion of the aesthetic, the spiritual, and the rigorously mathematical is a unique feature of the Japanese tradition, a testament to a culture that saw beauty and order as intertwined. The ultimate measure of Seki's influence is found in the generations of mathematicians who followed him. He was a fountainhead. His students and their students, forming the Seki school, dominated Japanese mathematics for nearly 2 centuries. They refined his methods, extended his theories, and applied his principles to new domains, from astronomy and calendrical science to cartography and engineering. He provided them with a robust framework and a symbolic language, empowering them to build a uniquely Japanese scientific enterprise. The intellectual vibrancy of the Edo period owes an incalculable debt to the tools he created. When Japan later opened to the West, its scholars and engineers possessed a formidable quantitative literacy, a foundation of analytical thinking that had been cultivated for centuries within the Wasan tradition he established. In the final analysis, Seki Takakazu represents more than a collection of brilliant discoveries. He embodies the principle that genius is a global phenomenon, untethered to any single culture or lineage. His life's work stands as a powerful testament to the capacity of the human mind to construct intricate and beautiful logical systems, to find order in complexity, and to push the boundaries of knowledge. The study of his achievements enriches our understanding of mathematics itself, transforming it from a singular historical path into a magnificent, branching tree of human inquiry. While the specific methods of Wasan have been absorbed into the modern global framework, the spirit of its greatest master endures. Kōwa Seki remains a figure of profound importance, a quiet giant of the East whose intellectual shadow stretches across the centuries, forever altering our perception of the history and the universality of mathematical thought.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.